Alright, hello friends. Let's talk a little bit more about how CPUs, specifically modern day CPUs, like to work. They have some cool things, and we will learn about them. So yeah, let's learn how in the world does our CPU execute the instructions that we give it. We say like, I want you to add these two registers into this register. Like, what really goes on? Right? We talked a little bit about it at a very high level. Let's go lower, okay? So I guess the first vague answer is that like so much goes on when the CPU is going through an instruction and trying to execute it, because like just think about it, it's reading it out of memory, right? It's got to do that at least, and then it's like in some weird encoded form, and it needs to be like turned into something the computer can understand. Like how do I know that these ones and zeros mean like add into x4, x1 and x2, let's say? Like how do you know that? It's got to figure it out. So it's really cool. It does a lot of cool work, and that work we say happens in stages. All right, so yeah, there's a bunch of stages that take up the time that you take to like execute an instruction. Again, that's very vague, and every stage we'll say takes a clock cycle to complete. So here's the idea. Like there's some stages for like, go get the data, go get the registers x1 and x2 as you're executing this add instruction. Like there's a clock cycle for that. Then there's a clock cycle to go and add them up in the ALU. And then there's another clock cycle to take that answer and shove it into x4, the register. So actually I lied to you. I technically lied to you when I said that it takes one clock cycle to run this instruction. But at the same time, I'm not lying to you. So I'm going to show you why I'm still correct later in this lecture. But you can imagine it's going to take a little while. I got to get these values, send them to the ALU, shove the answer into x4. Those are separate stages that we'll get into, and they each take a clock cycle to complete. Okay, so here's the clock, by the way. I drew it before, but here's like a detailed drawing of the clock cycle. The clock, the CPU clock, it's not like a something with actual numbers, but it's just going from 1 to 0, high to low, high to low. All right, it's just a signal. It's a clock circuit that goes, it's high for a little while, low for a little while, high for a little while, low for a little while. And we say going from high to low, that's one cycle. It's one clock cycle. And the reason this needs to exist is that it gives some time for all the electrons to like get far down their wires and go to where they need to go, because that takes the speed of light, and we have to wait at least that long for all the electrons to move into the registers if we're trying to save a value, for example. Like you have to actually consider that, which is surprising. Can't go any faster than that, otherwise the electrons will not have made their way to the register to actually save the new value in it. So yeah, just it's kind of like a waiting amount of time, and that lets everything propagate, and everybody's waiting for the next signal. All right, so once the clock hits 1 again, like it's time for the next stage of our CPU pipeline. All right, so everybody's waiting for that one there. Okay, I hope that makes sense. Again, if you want to know more about this, you're going to have to take a computer engineering class, because this is about as low level as we go. But at this level, let's keep going. All right, let's talk about the different stages that a CPU takes to execute an instruction. These are kind of pretend stages. They don't correspond to anything in real life anymore. They've been broken down further in modern day CPUs, but this is what I want you to understand. So memorize these ones. I don't care about you learning the actual stages of a modern day CPU. They can all be generalized in this way. Okay. So here's how your CPU executes like this add instruction. Here's what happens. Okay, so the very first stage of CPU instruction execution is it's got to read the data out of memory that corresponds to that instruction. That's called the fetch stage. All right, F for short. So that's where we get an instruction out of memory, and that's where PC is pointing to. Remember, so PC is like, all right, there's a register PC. It's holding the address of a place in memory. It's like somewhere. Like it's pointing here, let's say, and that's where the add instruction is. Add blank into blank, blank, blank. Okay, so that's what it's doing. And also remember that that instruction is a bunch of ones and zeros. It's 32 ones and zeros. So it's just binary, all right? So the very first stage, the fetch stage, is get that instruction out of memory and put it in a register, all right? That's called the instruction register. We'll talk about that on the next slide. All right, so read that instruction out of memory, get this in a register somewhere, so we can actually look at it quickly, because we know how long it takes to talk to memory. Okay. The next stage is once I have these bytes freely accessible to myself, and I am the CPU, I would like to decode those bytes. Like what do these 32 ones and zeros actually mean for me, the CPU? What is this instruction encoding? Is it an add instruction? Is it a move instruction? Is it a sub instruction? It is going to figure out what we're talking about, and then also the registers involved. It's going to decode everything, and like it's going to get ready to like do the addition if it's an add instruction. It'll set the control logic for the next stage to be like, all right, you are doing an addition on these registers, get ready. That's what the decode stage does after it figures out what everything means. All right, so it's doing all that. Then we have the execute stage, which is where actually the execution happens, right? If you're trying to add a bunch of registers, the addition happens here. This is where the ALU wakes up and actually adds the numbers, all right? Gets that result ready to go wherever it needs to go, okay? And now we have two final stages. Sometimes we don't have this one, all right? Sometimes we don't have this stage. Sometimes we don't have this one either, all right? So it depends. There's actually no memory stage for an add instruction, but you can imagine if we were executing like a load instruction or a store instruction, we were like computing the address to go to or something in the execute stage, and then the memory stage is actually going to memory, like talk to memory now, go get that thing, get the thing you're asking for, load it, or like write the thing you're trying to write from a register, store it. So that's the memory stage. Does not exist in the add instruction, so we skip over that. But for load and store, that's of course necessary. And then finally, if there is a result that needs to go in a register, that's called the write back stage. So the ALU is like doing the addition here, and we're writing back the result in the write back stage where we put our final answer in some destination register. All right, and this needs to happen last because we won't have a value until one or both of these have completed. All right, it's like we need the add instructions result, so the write back has to go after that. And then also if we're trying to load something, we need to like get the value out of memory, and then we're ready to put it in the register. So you have to like, that's the right order, okay? I hope that makes sense. So there's a million more stages than this. There's like 15 or so stages in like modern day CPUs, but they all kind of like correspond to like doing a piece of fetch, a piece of the decode. So honestly, it's a good idea to realize that, or not to realize, but to remember these ones, okay? Because everything can really be broken down into these basic categories, which is all that I care about you learning in this class. Okay, so let's zoom in on those stages. So the fetch stage, it's like, all right, PC's pointing here, give me that value out of memory, let's figure out what instruction it is. So that's the fetch stage. So PC, all right, PC's pointing to this address, and boop, connected across a bus from the CPU is our memory. And so we're gonna go ask nicely for what's at that address, and we're going to read it in. All right? We're going to read it into a special place called the IR, the instruction register. So the very first step of the fetch stage is like tell the memory to read from that PC address. Go to address 1234, give me that value back, please, and shove it there. All right? And this is called the instruction register, IR. IR stands for, that's supposed to be an R. The instruction register. Boop. Register. That's supposed to be a G as well. And that's going to hold the bytes of the instruction, holds the binary form. Because this is just ones and zeros at the end of the day. A bunch of ones and zeros. Holds the binary form of the instruction. All right. So yeah, the first step is to like go to memory, get the value, and like shove it here in IR, and then here it is, ready to go. All right, ready to go. It's still in binary format though. Okay, the book has just drawn it in a pretty way. So it stores it in IR, and it also increments PC to get ready to read the next instruction later. It's like, all right, we just read 1, 2, 3, 4. The next instruction right after this is going to be at address 1, 2, 3, 8. So let's get that one ready in PC. But we've got the current thing right here in IR. Okay, that's how that works. So get ready to do the next one as well. And then, okay, we have some bytes in IR. Let's decode them. That's the decode stage, remember. All right, that's going to like figure out what instruction we're working with, and then set up all the control logic to like hook in the right registers and the right output values, all that fun stuff. So apparently, the way that your book is going to represent an add instruction is like these are the operands, and then this is the register to write the answer back to. So it's trying to do that addition, all right? Addition on these guys, and then write the answer back here. And then remember that PC is pointing to somewhere else now because we've incremented it. Boop. So yeah, store the instruction data NIR. So let's see, read request to memory. Memory address is in PC. And then we store that instruction data NIR and increment PC. Important lines to underline. All right, so now our decode stage. We are, okay, we figure out, we have to decode the fact that this is an add instruction. So that we figure that out right now. And then we figure out our operand registers. So it's a little backwards to ARM, the way that your book is doing it. These are our operands. Register 1 and register 3, we're going to sum those guys up. All right? So you got to figure those out. Okay? And so we have to say, all right, get ready, ALU, like we're going to eventually send the opcode there. Get ready to do like an add instruction. And then also, our initial inputs is going to be register 1 and register 3, so it's going into the place where the registers live, called the register file, to like get those out and ready to go into the ALU next. All right, so it's hooking them up. It's hooking them up, and then out of here is like, this is register 1, this is register 3, hooked into the ALU now through multiplexing. Okay, so that's pretty nice. So like, this was the fetch stage, and now we're on the decode stage. I had to wait a little while for the clock to get us here. Okay, so we figured out the operation to perform and the sources of the operands. Okay, what next? Well, now we know it's an add instruction. All right, we know it's an add instruction because of the decode stage. We are ready to perform that actual operation by sending the add opcode to the ALU. And from before, we have those old registers like register 1 and register 3 hooked in to the ALU as well. That's all ready to go now by the execution stage. And then all that we do in the execution stage is like tell the ALU to do its thing, compute your result, and then get that ready. Get that ready because in the next stage of execution, I am putting that somewhere. I'm either using that to go to memory, or I'm writing that into a register. All right. So yeah, those are the first 3 key stages, and then the memory stage is sometimes it's optional unless you're doing a load or a store. All right. So this is reading or writing to data memory, all right? And so this is your main memory. So this is only for load and store instructions in ARM, at least, is when this happens. So when we go to the memory stage, and we need to do this before the execution stage, because you might have done something like this. You might have been like, load into, I don't know, W0, the value of X1 address plus 4. It's like there's a plus 4 going on. The ALU handles the plus 4. You see that? So like we might have needed to wait on that. That's why we do it after. So the execution stage needs to happen first, right? To compute this fancy address. Execution stage did addition for us. Isn't that so nice of it? Okay. So the execution stage figures out the address. That's why it has to happen then. And then yeah, this add example that your book is like drawing does not use the memory stage because it is only dealing with registers. Okay, and then once you have a value to put in a register, if your instruction requires it, there is a write back stage that stores the result. All right, so that is from the decode stage. We know that like it's register 0 that the target of this add instruction is. That's where we're writing to. So we're shoving that here into the register file. That's the register I'd like to write to. We give a selector value for register 0 to pick it out. Then we set the write enable high to the register file because yes, we want to write to this register now. And the data I want to write into that register that I'm selecting here and write enabling at the same time, it's all working out at the same time, is, all right, it's register 0. I want to change whatever is there. It was like 41 or something. I want to make it whatever I just got out of that ALU from the execution stage. All right. So that is 42 for my add instruction. Okay, I hope that makes sense. So you're just writing the value back. And we know how to make registers now, right? We like set the write enable, multiplex the register we're trying to figure out. Here's the data we want to write to. Here's the selector for the register we want to mess with. Like it's all what we've learned, but this is how it works. These are each the different chunks of execution. These are all the stages. All right. So I hope that makes sense, and that is that's how the CPU executes instructions in a nutshell. If you want to learn more, I'm forcing you to now take an upper division computer science class or a computer engineering class. All right, so yeah, these are very key stages that I want you to remember. Let's see, so you'll read about this in your book as well. And now let's move on to something called pipelining, because I told you like, oh, All right. There's like 4 stages. There's 4 clock cycles to run this add instruction, but I told you so long ago that it takes like a clock cycle, 1 clock cycle to run in every individual instruction. Was I lying to you or was I not, is now the question. So you might think after what I just told you that I was lying to you. But in fact, I actually wasn't. And there's a weird reason, all right? So let's talk about washing machines, and we'll learn, all right, why it really does take a clock cycle to run these instructions, even though they take 4, which makes no sense, I know right now in your mind. I understand. We'll get there. So here is a silly metaphor. So it takes 30 minutes, let's say, 30 minutes each to do a load of washing, to put everything in the dryer and do the dryer. It takes 30 minutes to fold your laundry, and it takes 30 minutes to put away your clothes as well. 30 minutes for all of that, so like 2 hours total. If you have 4 loads to do, would you do it like this? If you hired 4 separate people, one to do each job, what's the problem with this sequence? It's like, all right, person A does 1 load, person B does another load after that one's finished, person C does another load only after that one's finished, person D does your 4th and final load of laundry after all that's done, and then like it's 2 a.m., now you have your clothes. What's wrong with this? Do you see it? This is a lot of just wasted time, isn't it? Because like the second you're done with this washer, you could use it at 6:30. Yeah? So everything could be shifted that way. Do you see it? Do you see it? So like that could be here. And then same for this guy. Like, all right, it'll be 7 o'clock by the time this is all ready for a new load of washing, and then everything else doesn't overlap, right? You're good. You're good. You can have your 4 separate people just be in charge of one thing, and then you will finish by 9:30, yeah? Rather than 2 a.m. Does that make sense? I hope that makes sense. 1, 2, 3, yeah, I'd be done by like right here. It's like the new end time rather than the old end time that was 2 a.m. Okay, so isn't that nice? That makes a lot of sense. Okay, we're going somewhere with this in the CPU as well. There's no reason to like wait until the clothes are put away to start the next load, right? If you have available execution power, you should use it. And now we can come back to these stages. There is no reason to do your instruction and do the fetch, decode, execute, memory, write back, and then the instruction after that is waiting, and only after all this is done do you do fetch again. Makes no sense. So this is called pipelining, and the idea is to treat this like the CPU pipeline. And like this is instruction 1 running, this is instruction 2 running, instruction 3 is like all your 4 instructions you want to run on the CPU. Boop. And this is like the fetch stage. Decode, execute, write back, fetch, decode, execute, write back. Do you see that the circuitry that does fetch in the CPU is completely separate from the circuitry that does decode and execute? It's like a washer versus a dryer. So once you've done the fetch stage for instruction 1 and you're moving on to the decode stage, the fetch stage is available for instruction 2 to get started. Does that make sense? You are running multiple stages, different stages of multiple instructions at once. That's what we can do in our CPU. That's how we make things faster. We increase throughput. It's called pipelining, all right? And then suddenly you're running 3 instructions at once. Suddenly you're running 4 instructions at once. And at this point, every clock cycle, you're completing an instruction execution. Does that not blow your mind? That's amazing, okay? That is called pipelining. So let's talk about that, okay? So we want to replace this, like, okay, do all of the fetch, decode, execute, write back, fetch, decode, execute, write back. Do them all in order and just wait, right? Only after the write back stage of instruction 1, of the blue instruction, can we, like, start the fetch stage of the red instruction. That is dumb. Let's fix that by pipelining. We want to do this instead, all right? The very first cycle that your CPU turns on, it's just doing one thing. You got to start in the fetch stage, and that's busy. All right, that's the first cycle. So you start fetching the blue instruction, and then it's time to decode that blue instruction. Yeah, and so the fetch stage is ready to do the next one because it's got available processing power. Okay, so that's how that works. And then by the time you're in the third instruction, like you can be fetching the green one, the third instruction, executing the blue one, decoding the red one, all right? And then you have so much extra space, so much extra time. Then you're writing back the original instruction, the first instruction, executing the second one, decoding the third one. Now you're fetching the fourth one. And by the time you hit the fourth cycle, always, there will be a write back stage that is in use. And so an instruction is completing execution by the time we hit the fourth cycle of our CPU after we turn it on. From every cycle after that, we're always going to have a write back stage in use, and we're going to be completing the execution of an instruction, all right? So yeah, just wait a few cycles, and then really every instruction, every clock cycle, we are completing instruction execution. So I didn't lie to you. Haha, even though it takes 4 clock cycles to run an instruction, because of pipeline execution, we are increasing throughput, and that allows us to actually complete instruction execution every clock cycle after a warm-up phase, which is very short, okay? Isn't that nice? Oh man, I love this. So this is what real CPUs look like these days. This is a fancy semi-recent ARM processor. Here's what its pipeline looks like. It has it takes 5 clock cycles to do all the different instruction fetch stuff. So like it's broken down fetch into more than just one thing to do. It's a little bit fancier. It takes 3 stages to decode, 3 clock cycles to decode, and then it's doing some weird stuff called register renaming. This is getting ready for execution, essentially. And then I have no clue what this actually means. We can look it up together one day, maybe. And then by the time we get here, now we're actually doing like... it potentially takes a few clock cycles to do different things. Like to do an add instruction versus a multiply instruction, it takes longer. Same with like division. It takes a little bit longer. And so they split things up like this to make certain instructions take less time. And then finally there's a write back stage. All right. So it's about 15-ish in the best case clock cycles to run an instruction these days. 15 different real stages, but they can all be broken down mostly into fetch, decode, execute, memory, write back. Okay, so yeah, that's what modern day CPUs look like, but it's still worth it, absolutely worth it, to understand the basic idea. Okay, you can go fancy on your own time. So yeah, there is though an issue. There is a slight issue when you're trying to branch, or when you are trying to use data that needs to be like the previous instruction is dealing with or creating. Okay, it's called a stall in the pipeline. These are fun metaphors. Sometimes our pipeline has to stall because it doesn't have enough information to compute the answer yet. Okay, so take these for example. We have to stall due to, it's called a hazard. It's funny. It's called a data hazard for this case. So for example, if we want to do this, we want to add, like this adds R1 and R2, pretend those are register names, into register 0. R0 is going to hold the answer once this is finished, right? Once we hit the write back stage, R0 holds the answer. Boop. But this instruction that comes right after it, do you see that there's an issue? Because it's trying to use R0 and add the answer into R3. So this instruction needs this value for R0. This value for R0 is only set here, but we need it here. That's the execute stage, right? We need to do the addition here. So I'm trying to use a value before I have it. This is impossible, all right? So we cannot do it like this. We have to wait. We have to push this execution stage after this write back stage. Does that make sense? Because we don't have the right value yet. The only value, we only get R0 set in the write back stage. We don't have the right answer until for this addition that's needed here. We don't have it until this is finished. So at best, we need to push the execution stage to be right here. That's the idea. Okay, so it needs to move. This needs to move to the right. Okay, and so what has to happen is we stall the pipeline, is what we say. All right, another metaphor is like we bubble the pipeline. We bubble the pipeline. Like send air through it instead of actual information. Just for a second until it's ready to do its right thing. So now we have correctly waited and we have the data that we need and we can do the execution stage. So sometimes you do have to wait like this, but if you arrange your program well, you can minimize what happens here. All right, so yeah, these are called hazards that make you stall your pipeline. The easiest example is this kind of add instruction, this chained add instruction thing, where it's a data hazard, and that means that the data that we need for this instruction execution just isn't ready yet. We don't have it ready, so we have to stall. We have to bubble the pipeline, right? The other kind of, the other reason you'd want to stall your pipeline is for control purposes. It's called a control hazard, and that's when you're executing a branch instruction. You're saying something like compare like x0 and x1, and then like branch less than or equal to some label. And then like if you fell through, like you do your add instruction, add, I don't know, add x0, x1, x2. But if you branched, like you would go way down here somewhere. Okay, so this branch could either go one of two places. It could go here, or it could jump you way down here somewhere. All right, does that make sense? And so you don't know, right? You don't know where to go by the time we're ready to like fetch and decode this add instruction. I hope that makes sense. So let me try to spell it out. Kind of think of what's going to happen here. We do the comparison that sets the flags, then we do a BLE label, all right? And this could either be taken or not taken. And so as we're working on this branch, we're trying to fetch the next instruction, and we don't know which one to fetch, right? Because either we take the branch, we haven't taken it yet, because that happens on like the write back stage that like does the write back to the PC. We are trying to execute like the next thing after this. We're trying to fetch it. We don't even know what to fetch, because like it could be this add, or it could be this place way down here if we took the branch. Do you see that? We have two options. We're not sure what to fetch yet until we get to like the write back stage of the BLE. All right. So that's how that works. You have to wait until the branch sets PC. And so again, you need to stall for a little while. All right. There's ways to get around this, and one way is called out of order execution. All right. Here's the secret to try to keep this idea going of like execute one instruction every clock cycle, because the stalls bring you down again. So one way to fix it is to do what's called out of order execution, and involves the word superscalar, which is a fun word to say. So here's the idea. Here's the secret. So we have superscalar processors these days, and this is going to help us try to execute one instruction every clock cycle. So I can best define superscalar by first defining scalar. All right. So a scalar processor is one that can complete at most one single instruction per clock cycle. So there's only one instruction at the write back stage any given time. That's a scalar processor. That's exactly what we've been talking about. This is a scalar processor. It can at most do one write back every clock cycle. Right. A superscalar processor, on the other hand, kind of looks like this. It has, in the same core of your CPU, the ability to do a couple fetches and decodes. It can work on multiple instructions at once. It could potentially be doing 2 write-backs every clock cycle. Okay, does that make sense? So, like, here's a processor core, and it has multiple ways of executing instruction. It has 2 separate little mini CPUs essentially inside the core. It has 2 separate register files, for example. Register file 1, register file 2. It has the ability to like talk about 2 different sets of registers. It has the ability to like mess with and do 2 different execution stages at once. So it's got 2 pairs of pants here, right? Boop. It's got ALU1. It's got ALU2 because it could be doing 2 execution stages at once. And so it's got 2 of everything. That's a superscalar processor, all right? It can finish off more than one instruction every clock cycle by increasing the number of execution units. So it's got multiple copies of registers, multiple ALUs instead of just one. So like, and then it's able to do 2 each of these stages: fetch, decode, execute, memory, write back. All right. And this is, by the way, this is not the same as multi-core. This is all happening in the same processor core. All right. This is not multi-core yet. So that's pretty cool. Like 2 fetches, 2 decodes, 2 executes, 2 memories, 2 write backs, and then it all can be chained and pipelined. All right. So this is to help with stalls, because we don't like stalls, and so it's trying to do a couple of these at once to like not waste time and like average to be 1 instruction every clock cycle. So that's really nice. So that's one thing that it's good at. And then also superscalar processors tend to do what's called out of order execution. So also, in addition to all this, in addition to trying to do two at once, the CPU is looking ahead and taking instructions not in the order that you wrote them as the programmer. It's trying to execute them out of order if it can, to save time later. All right? I know this is wild. So let's talk about it slowly. So here is another thing. In addition to having multiple execution units inside of one processor core, the CPU is also doing this. All right? It's doing out of order execution. And this is what it looks like. All right? So here's a silly example. Let's say that our registers are called R registers. With normal execution, let's say that it takes a while to do a division. Division is a hard problem. It takes a few clock cycles to do a division in a CPU. So that one takes like 3 or 4 clock cycles to run that line 1. All right, and then the rest you normally think of them being done in order. It'll take this long, right? It'll take from here to here to run all these instructions. Instruction 1, the division takes a while, and then the rest they take like 1 clock cycle, let's say, to run to completion. So if you executed these instructions in order, it would take this much time. All right, we can actually save a little bit of time though. All right, assume it takes that many cycles, 15, let's say, who knows, because it's complex. The rest take like 5 or something, but you can think of it like 3 versus 1. That's cool too. Okay, so we can save some time if we use a superscalar CPU that can execute multiple instructions at once, right? Let's say, like if it can execute 2 instructions at once, lines 2 and 3 they can run at the same time, can't they? Because they're touching different registers. R1, R2, R8, R5, constant 1, R5 again. Those 2 lines don't mess with each other, so we can run them both at once in our superscalar CPU. All right, superscalar core. So 2 and 3 could run at once, and then the rest of these are like waiting on each other. Like R6 depends here, R4 depends on this guy. So you're forced to run the rest in order. But you can double up on 2 and 3. All right, if you had this way. You got a 2-way superscalar CPU. Executing these instructions still in order though. So we've saved some time. All right? So that superscalar can do us that. It can save us a few clock cycles. We can get an even better savings though if we think really hard about how to execute these guys in the best possible order to retain the right answer, keep the right answer, but like don't do this in the same order that the programmer gave it to us in, because maybe we could make things faster on our end. All right, so if we had extra stages, if we had like the ability to do 3 instructions at once, so like 3-way superscalar, and we also were able to do things out of order, we can shave off the most amount of time. Here's the best you could do. All right, so these guys, you see 1 and 2 kind of like have to happen in that right order. 1 has to come before 2 because 1 writes to this one reads it. So 1 and 2, they have to wait on each other. 1 has to happen after 2. Or sorry, 2 has to happen after 1. And then same with like 2 and 6. Those have to happen in that order. So like it's gotta be 1, 2, 6 in that order. You see that? The rest though, they don't really do anything. They don't really do much else. We got I guess 3 and 5. 3 has to come before 5, but they could all be happening like at the same time, right? 1 and 3 could totally be happening at the same time. See that? And same with 4. 4 needs to come before 5 because like we have this kind of relationship. It writes a value. This reads that value, but at that point, like it doesn't matter. It could be happening at the same time as 1 because 1 and 4 don't like deal with each other, right? Same with 1 and 3. So we could be running instructions 1, 3, and 4 at the same time, if we could do that. And then 5 has to come after 3, so we can put it there. And then 2 is waiting on 1, so we need that there. And then 6 was waiting on 2. So like that's as good as we could possibly do, all right? But like we could double things up there. We could triple things up if we had even more execution units, okay? It's called out-of-order execution, and that's what most modern-day CPUs are using these days to try and save as much time as possible for you, all right? Which is great. Time is money. So yeah, here's how it works. Here's how the CPU is like looking at all these instructions and figuring out, it's looking ahead and trying to figure out like what's the best ordering that keeps the right answer but saves me time in the long run, all right? Here's how it works. It's going to track these ideas that we've been talking about. It's going to do the color coding. It's going to figure out like what can come before what. What's the best thing we could do here? So these are called data dependencies. It's going to track those dependencies between like pairs of instructions, all right? If there is a dependency, that means you cannot change the order. You can't make them happen at the same time. One has to come before the order. One has to come before the other, sorry. So here are your kinds of dependencies that exist in code. You have this is one we've been talking about a lot so far today. This is called a read after write dependency. So it's this, raw for short, all right? This is saying, all right, we are writing to x0, and then we're trying to read from x0 right after, so we need this value. We cannot swap these instructions. You see that? Because if we did this one first, we'd be getting some old value of x0 that's not the one we're trying to use for real. Okay? You cannot swap these instructions. They cannot be executed out of order. This one must wait on this one. All right? That's a read after write dependency. You have the flip-flop as well, write after read. So yeah, first, did I explain this well enough? So a read after write is like you're not ready to read this. It doesn't have the value until this is completed. Okay. So yeah, the other kind is write after read. So again, we have x0, but in a different way. All right. So this is trying to write to x0, and this is trying to read some value of x0. But again, do you see that you cannot swap these guys? Because if this one came before, it would be writing x0, and then this read to x0 would be getting a different value, not the one that it needed. Okay. So again, cannot swap these. This one must happen before this one, right? You can't write something until everyone who needed that old value, like this guy, is finished reading from it, all right? So you can't swap these guys, can't do them at the same time either. All right, what about write after write? That's the last kind of dependency, okay? So this is another fun one. You cannot swap these guys. They're both writing to x0, and the reason you can't swap them is because you have to think about what's below, right? The stuff below is banking on this value being an x0, the one that is being computed here. See that? So that's very important, all right? This x0 value needs to be the one that's propagated down here. Otherwise, if we swap this one, if this one really came down here, we'd be getting a different value for x0 that every other instruction sees. Do you see that? That's not good. So yeah, the second write, this needs to happen second. Otherwise, everybody who depends on that value down here is like missing out. It's getting the wrong value of x0 if you swap these guys, okay? Yeah, everybody down the line is getting the wrong value otherwise, okay? So with that in mind, I've taught you about a bunch of different dependencies, these guys. You got read after write, write after read, write after write. Try to find these dependencies, all right, between these different lines of assembly. So here are some lines of assembly. Try to like find the dependencies between them, or you can just like write down numbers, whatever you want. So you got read after write, write after read, and write after write. And just like draw an arrow if there's a dependency. All right, kind of like I'm doing here. Draw an arrow from one to the other. Like you cannot swap these. They must remain in that order. And if there's multiple dependencies between the same pair of lines, you just draw one arrow. Okay. So let me do one for you, for example. Like here are dependencies, and I want you to try. Take a minute. It's really gonna help. All right. It's really gonna help you. So here's. That's the best I can do, I guess. So there's those guys, and let's do one together. Okay, so here is a read of x2, and here's a write to x2, and so that is a write after read dependency, isn't it? And so there's we cannot swap 1 and 2's order. Okay, that's cannot be any better than that. All right, so pause the video, give this a try, and then I'll show you how I think about this. All right, so yeah, let's look for our dependencies now. Is there a dependency between 2 and 3? Let's just like look at every pair, kind of. We have, oh yeah, I see x5 being, no, that's just read and read, that's fine. But I see write to x2 and write to x2. See that? So that's a write after write. Boop. That needs to be in that order. And then what else? What else? I see x0 some more. Like here's x0. This is a read of x0, or sorry, a write to x0. This is a read, so this is a read after write, and so 1 and 3 as well need to be in order, and it's kind of redundant because 1 and 2 and 2 and 3 together like kind of tell you that you can't do 1 before 3 or 1 after 3 anyways. That's kind of the idea. And then if you stare at this long enough, you notice that like there's a big chunk of things here that like the rest of these don't even touch these registers. So they could be done at the same time in parallel. So we got, let's see what next. x6, so what is that? A read after write dependency. Same with x11, read after write. Got some X7s. Got a dun, dun, dun. This is like a right after read. Boop, just like that. I'm sure there's more. What else? No, I think that's all I can see. And then here, 8, 10, and 9, again, kind of separate. All right. So yeah, those are all the dependencies, and you can kind of see like, all right, what's the best order now? Okay, let's figure this out together. So let's see. Can I copy? This is a big question right now. Can I copy and paste all this? Let's see what I can do here. I think if I do it this way, it'll work. Yeah. Bam. All right. So there's my my instructions. Now let's reorder them together and try to get as much speed as possible. Draw like a picture like this. All right. Let's figure it out. So let's pretend we have let's maybe pretend we must execute them in order, and it's got to be superscalar. All right. And we can also do out of order as well. Okay. So in order, superscalar, or even out of order. All right. So let's go crazy. Let's do as much as we can out of order, even. Dun, dun, dun. Let's see. Yeah, let's just say that's what we're doing. So you have out of order, superscalar. Whee. Did I spell it wrong? I did. AR. All right, so for example, let's see what we got here. We've got 1 and 4 could happen at the same time, right? Because they don't touch each other's registers. Like 1 and 4 could totally be happening at the same time. Dun, dun, dun. 1 and 4 could totally be happening at the same time. Let's see. And then 7 can also be happening at the same time as 1 and 4 because like they're not touching each other's registers. So, like these guys could all be happening at once. Just pretend it takes the same amount of time for all of them. And then 1, 2, and 3 got to go in order. 1, then 2 has to happen after 1, then 3 after 2, and then 4, 5, and 6 got to be in order. 4, 5, and 6. They have to work like that, right? 4, 5, and 6. They got to be in that order. But that's about as good as you can do. I hope that makes sense. So yeah, look at all the time I'm saving. It's like start here, end here. That's a lot better than doing them in some all at once, right? Having everybody wait on the others. We've saved a lot of time there. And if we wanted to rearrange, let's say we only had like one execution unit inside of our processor, if we wanted to rearrange all these guys in the best, most efficient order that's going to minimize stalls, then you can kind of read it like this. Whee! Or this is an arrow. You could kind of do this kind of this out of order execution. 1, 4, then 7, then 2, then 5. Do you see how this would minimize all the stalls? Because like we're spacing things out. 2 and then 5, then 3 and then 6. Because like we have these dependencies, like 1 better happen before 2, better happen before 3, but we're spacing it out so that like everything is getting in the right spot first. And then 4, 5, and 6 kind of depend on each other, kind of like that. And then 7's all alone. So it can go anywhere. So like if I had to rearrange them, like that would be the best rearrangement, all right? And then also if I could just put them in any order, and like if I had as many superscalar units as I wanted, 3 would do the trick here, and I'd finish them as fast as possible. Okay, there's kind of a correspondence between here and here, if you think about it long enough. That's more or less kind of what I wanted to show you. I hope you get a feel for like how you could do this, all right? How the CPU is trying to do it too. Okay. So yeah, with that, let's talk about trade-offs, because I told you like, okay, our pipeline, like the book pipeline is 5 long, right? It's got 5 things to do. Modern day CPUs have a longer pipeline. Where's that picture? Maybe like 15 to like 20-ish clock cycles, 15 to 20-ish things to do in the pipeline. And there are trade-offs to each different one. All right. So when you make a longer pipeline, that means you have less to do at each stage, which means like you can have the CPU switch over faster because you don't have to move information as far. All right. The clock speed could be faster, which means that the CPU itself is faster. It doesn't have to do too much. It doesn't have to move things from far away on the CPU to somewhere else. Okay. So that's a pro of a longer pipeline. But also a con is that if you have a long pipeline, when you stall, you're not just bubbling, you're wasting a couple clock cycles, you're wasting like 10 clock cycles maybe. All right? So there's a give and take there for sure, and that slows down the CPU. And so just empirically, in practice, every CPU these days is like figured out that about 15 different stages of our pipeline is a good number. That's kind of the sweet spot as far as modern day CPUs are concerned. But maybe this will change one day once we learn more. Okay? So yeah, that's out of order execution in a nutshell. Our CPUs these days, oh man, are they fancy. They're doing such cool things. All right? And then finally, I like to talk about something called branch prediction, which is a very, very cool idea. And it will help us with the other kind of way that we stall the pipeline. Like everything I just told you, most of it, out of order execution, superscalar, that's to kind of prevent data hazards. Control hazards, I haven't really told you how to deal with yet. Because it's like, we're doing this branch, like we really don't know which instruction to execute. Is it the add or is it the thing that the branch takes? Like, do we do that or do we not do it? So let's figure it out. The secret is to do both, or make a really good guess. Okay, those are your two options. So branch prediction is all about guessing which side of that branch to go down. All right. Modern CPUs, they do not stall when they see a branch instruction. Instead, they're like, all right, this guy could go here or here. My branch could either fall through or jump to here. I'm gonna guess. All right. They're just gonna make a good guess at which side of the branch will execute. All right. Be like, all right, I think it's going to be this side. And so I'm going to fetch this instruction and start executing this instruction. Okay? Which is wild. It's like, I don't even know if I'm right. I'm going to try to run this instruction, though. All right? So they start executing the predicted side of that branch, and it may or may not be the right one. You don't know until you get to like the write back stage or whatever, till the execution stage of the compare instruction, or the branch instruction itself, sorry. They're just like going to pretend I'm taking the branch. I'm going to pretend we're going to do that. Let's execute this instruction. It's called speculative execution, because it may turn out that we really needed to go over here and run this instruction. But if we didn't, right, if it was a good guess, then we wasted no time. You see that? So if the prediction was incorrect, the CPU has a way of throwing away all the work that it's done. Like, all right, this is writing to a register. Oh, we weren't supposed to do that. Let's unwind. Control Z. All right, it's possible for a CPU to do that. And that's still good, right? They would have done nothing otherwise, right? The CPU would have just been waiting, bubbling up the pipeline. So there's no harm done for trying one branch versus another, okay? And the way that prediction happens is there's like a table, all right? There's a table that's getting made inside of the CPU. So it's like it remembers the address of each instruction, and it's remembering like how often like the branch was taken or not, how often like it took the jump rather than it fell through, right? Number of times that the branch was true or something, right? The comparison was true. So like, all right, for instruction number 1, 2, 3, 4, we took the branch 42 times and we didn't take the branch 5 times, all right? For instruction 2, 3, 4, 5, we took the branch only 1 time and we fell through 17 times. And so it's kind of keeping a running record kind of like that. And it's remembering like, okay, if I ever see this instruction again and I run it in a loop or something, like I should take the branch. Or if I see this one in a loop, I should just remember to not take the branch, right? It's better to fall through. And that's usually going to be the right answer. All right, so it's just like keeping a score like that, more or less. And it's greater than 97% correct on average. So it's really picking the right one most often, okay? So that's really, really nice. And if you think about it, in a loop, like it's always like, most of the time, right, if you're in a loop, for int I equals 0, I is less than 10, I plus plus, the branch predictor is like, it's usually, like you're taking the loop, this condition is always true, right, 10 times. So the branch predictor is going to be like, let's just pretend we're always taking this loop, because the only time that we have to like stall and we got it wrong is when the loop is over anyways. Okay, so usually, like when you have a comparison in your program, it's usually always going to be the same for a long, long time, okay, until the very end of your loop maybe. This is going to be a true branch most often, okay? That's kind of what it remembers. That's called branch prediction, okay? So it makes our CPUs very fast, and we really do more or less get this speed up. We get an instruction completed every clock cycle because of everything we've been talking about today. All right, this bubbling, I told you how to manage data hazards, and I've now told you how to manage control hazards. Isn't that nice? CPUs are really good these days for a lot of reasons. All right, so yeah, let's talk about the downsides of branch prediction. Like, it's really good, it speeds up our programs, but in certain scenarios, certain scenarios where security is very important, there could be an issue with you using a branch predictor in your CPU. Okay, so this is horrible. A hardware bug is horrible, or hardware vulnerability is a horrible thing to have because you can't really fix hardware. So this happened back in 2018. There was a hardware vulnerability called Spectre, that's what they named it, that affects pretty much every CPU under the sun, and nobody's going to fix it because, like, we love branch prediction. It makes our CPUs faster, right? So back in 2018, pretty much every CPU is affected. Oh no. What does it mean? What happens? All right. So what Spectre does, it's a vulnerability that allows you, if you have access to the CPU in this way, or if you just write a carefully constructed program, that's what I should say. If you write a carefully constructed program and you time it, you can do some nefarious things, right? If you were to time a program, that would tell you if your branch prediction was successful or if it failed, right? Because your branch predictor is always trying to go down this side or go down this side. If it messes up, it takes longer because you have to undo what you just did and go down the other side. Does that make sense? All right. So you can time a program to see if the branch prediction was successful or not. And if you write a program that branches based on private data, even if it doesn't print out the data, if the branching was done based on, like, the letters in a password, something like that, like the private key of somebody, of like a very important web server or something like that, if the branching of that program that you have the ability to time was based on private data, and you were able to time it, you're like, okay, yeah, it took the branch, that means it was a 1 bit there, or it didn't take the branch, or it stalled, that means it must have been a 0 bit there. You can recreate that private data. All right, so go look up the Wikipedia page for this. There's a whole lot more that I just don't have time to explain. It's also over a lot of our heads right now, including mine. It's a very, very fancy thing, but it has to do with branch prediction, and it allows you to recreate private data. I guess that's what happens when you use a branch predictor. You're able to do this. Hopefully we can craft our programs in a way that it's not affected by this. But yeah, that is a hardware level vulnerability. It's crazy to think about. All right. And so yeah, I think the last thing I want to tell you is about your next homework. Let's release that. Pay attention to that due date. But here it is. It's about out of order execution and superscalarness. All right. So here are 3 programs. Just doing a bunch of add instructions, why not? All right, so we'd like to, for each of these programs, pretend they're separate programs, we'd like to perform out-of-order execution on our CPU to minimize the number of pipeline stalls, all right? So I have 2 steps for you for this homework. For each of these 3 programs, I'd like you to draw every dependency, all right? Read after write, write after read, read after write, write after write. I don't know if I said them all. There we go. That should be all of them. Draw those arrows just like you did here. All right. So do that for each program, please. And that will allow you then, right, to do what I just did, kind of here, to give a very good order for these instructions that tries to space them out as much as possible and minimize stalling. All right. So like draw these 2 pictures and you can kind of read off the answer. Okay. So that is the first step. Draw the dependencies, and then with that new information, rewrite the programs to minimize the stalls on that pipeline. All right. So space them out just like I was doing here because of the dependencies. That will give you this kind of new reordered sequence. Okay, so yeah, that's what I want you to do for homework 1. It's not too horrible, but that's what I want to see. All right, so good luck with that. Yell at me if you have any questions. It's definitely going to be this example all over again, though. That's going to be what you use as you're doing it. But yeah, I think that's all that I wanted to say for today's lecture. A nice one about CPU design. And I will see you in the next one.